Okay. Let's talk. All right, so we've seen the two really big ones, body-centered cubic and face-centered cubic, and we've looked at them in kind of perspective view. That's the way that we're mostly going to look at, but there's a couple of other things that we want to do with that. We have two other representations. We're going to see if, with the limit that you can do with a pen on a piece of paper, if we can make that happen, because it is tricky to see. So I'm going to show you how cubes relate to hexagons, because it doesn't look like they do, but they do. And in your hexagonal close packing, you make a tiny adjustment to the way that the spheres sit on top of each other in layers, and all of a sudden you're a cube. But you can still see the hexagons, but you're a cube, okay? Because you have to look at it at an angle in order to see it. If you look at it from the plan view, don't know if you know this, but a 3D object, a representation of a 3D object. So here's a box. This is called its elevation. That's called its side elevation. And then this is called its plan. And so if I wanted to represent this three-dimensional box, I could show you just three pictures. This rectangle, that rectangle, and this rectangle, and label them elevation, side elevation, plan. And then you would know the plan is when you look at it only this way. The side elevation is when you look at it only that way. And the elevation is when you look at it only this way. And therefore I can construct a 3D box out of that. Okay. So we draw that either isometrically with the 30-degree angles, but more likely as the perspective of this 45-degree angle here. There is a way that we could just show a projection, and a projection is to take a three-dimensional object and convert it into two. And we do that by looking at the plan and then slicing through it. So if I look at the plan from the top down, I'm going to have a number of layers. The bottom layer, the one furthest away from me, is called 0. And the one on the top is called 1. And somewhere between 0 and 1, there might be something in this box that if I sliced it, I would hit. And if that something is halfway in the middle, then that layer would be called half. Okay? Let's look. What I'm going to do now is called a unit cell projection. And today we're going to see some fairly complicated unit cells, a little bit up from just sodium chloride and cesium chloride. We're going to now start throwing the other other ions around, and perhaps not having a one-to-one ion relationship. So instead of being sodium plus chloride minus, what if I gave you magnesium 2 plus chloride 1 minus? Now the number of minuses got to double the actual number of ions in order to make the same number of minuses. So in a face-centered cube, I have, no, okay, let's start with something easier. That F is now a B. In a body-centered cube, like in the cesium chloride, it changes nothing. All I did is change the F to a B.
Yeah, but I'm running Infinite and I scratched out the top corner of my cube, so I'm starting over.
But it's the same. Everything's the same.
Yeah.
Oh, never mind. All right. And then, because I haven't done any damage yet. And then I put my cation at the center. Okay. And it's useful for us if we have multiple colors. If you don't have multiple colors, hey, doesn't matter. You can find a way around this. Okay, I'm going to look at this in layers. So my eyeball, use my eyeball, is going to look at it here from what we call the plan view. Where this cube unit cell is touching the table surface, that's layer 0. The thing closest to your eye is layer 1. Between layer 1 and layer 0, there really isn't anything going on, except there's a cation bang at the center of the cube. That's layer 1/2. Okay. So this is a perspective unit cell diagram, and I'm going to convert it into a unit cell projection by looking from the top down. Okay. At layer 0, there are anions. Remember, this could be, I'm going to erase this one. This could be cesium chloride. So at layer 0, there are anions at every corner. On layer 1, there are also anions on every corner. But if I'm looking at it vertically, I cannot see these zeros, these layer 0 anions, because they're completely eclipsed by those. So I write that there is one of those at every 0 and every 1. And sometimes those are in parentheses and sometimes they're not. I think it depends how crowded you get, whether you would want to put them in parentheses. And then, at the center of the atom, see, if you're only doing this, I have color, so I can make the cation be red and the anions be black. But you could make the anions be hollow circles and the cations be filled in circles. There's always a way. That is at layer 1/2. Okay, so this diagram can now replace this one. Sometimes this is a fairly easy one to draw, but There are times when, you know, your drawing skills are a little bit off, and that red dot doesn't look like in perspective that it's truly at the center of the cube. It might be, oh, is it on the back face of this one, or there? This doesn't really have very much ambiguity to it. Okay, let's do it again. Let's do a face-centered cube, like we saw for sodium chloride. It's a passable cube, but it'll do. All right, so things that we know from this. This, again, has ions at every corner. These happen to be the anions. Although it would be possible, and we'll talk about it later on, to just, out of concept, shift this unit cell half a frame to the right, in which case we would exchange the positions of the ions. Okay, and then we have ions at every face. This is where, when you're writing in perspective, you get a little bit tricky. So I've got one on the top and one on the bottom. I've got one on the left face, and one on the right face, and then one on the back, and then one slap down in the middle of the front, okay? Those ones, unless your drawing skills have been practiced, might not be so great, might not be so obvious. And this is where a projection might help. Okay. And then, I've got my cation. In an octahedral coordination at the center of that cube, and then one on each edge. That one's a little bit off. I got one on the back. Okay. Yeah, that's right. Okay, let's do the projections for that. This is layer 0. This is layer 1. Layer 1/2 is in the middle. And all the action in this unit cell is either on the top, on the bottom, or exactly in the middle. There's no other place. Okay? So, looking, plan view. Here's my eyeball. Looking directly down at that, I can see anions every corner. And those corners, what layers are they on?
1, 0.
So I go 1, 0, 0, and 1, 0, and 1, 0, and 1. And then I have anions at the center of the plan view face, right here. What layer are they on? That one and this one. So that's also a 0 and a 1. And then I have this anion, which is on the center of the face to the left, the center of the face to the right, the center of the face at the back, and the center of the face at the front. These are all in the middle. They all get labeled as belonging to the layer 1/2. Okay. Let's put the sodium ions in. Sometimes, when you're looking from the top down, you will see that here's a sodium ion, and there is another one completely eclipsed by it on another layer. So when you write those ones in, they're going to need 2 numbers. And sometimes, when you see one, it's on its own, but it's sandwiched between 2 anions. Let's do these 4 first. This one has another cation immediately below it. But you know what else is on that parallel? Now our perspective diagram didn't quite catch that, because that circle, which is supposed to be center of my back face, is also on that vertical line. This cation eclipses that cation, and that big anion is also on that vertical. So we're going to have multiple things on the vertical axes. So now, I'm going to do a different pen. Do I have a different red? Yes. The red dots, what layers is it on? 1 and 0. And this red dot is at 1 and 0. I did it 0 and 1 before. Let's keep it the notation the same. My bad. Now, if you find this in a black and white text, where the dots are black and other dots are round circles, they will write one of the characters in bold for the filled in dot, and then the other one just regular, or even just the outline of the letters for it. So this is at 0 and 1, and 0 and 1, and I have a dot here. 0 and 1, and I have a dot here. 0 and 1. And then I have these ones, these red dots, 4 of them on the edges at layer 1/2. Oh. Yeah. They sit here. If you're doing this, you don't even have the dots. They could be an X and a circle. If you have 3 things, and we are going to have 3 things, you could have an X and a dot and a circle. You can make this happen with more, without the need for color. So 0, 1.5, and then what have I got here? That is this dot, which is at the half. And that dot is at the half. This dot is at the half, and that dot is at the half. Which leaves us only 1 dot remaining. Which dot is that? This one at the center, the body center of the unit cell. That sits here. So you could decipher that. If that's a bit much for you, you can, in turn, break it down into, because there's only things happening at 3 layers. You could say that this is layer 1, that is layer 1/2, and this is layer 0. That will also do. Okay? Let's look at some slightly more complicated unit cells and count their occupancy and see if this idea of a projection, which looks really, really nice and simple for this one, but then a little bit ugly and complex for that one, let's see if it's worth our time doing this. Now, if this one gets out of hand, you can always break it down into the individual layers. Okay, let's look at fluorite. Fluorite is on the screen. I like this one right here. Let's see if I can just, can I open the image in a new tab? Yeah. I might even be able to make that bigger. So you can see it when you read it again. All right. Selfie time. This is fluorite, and this unit cell is different than the cells that we've seen before in one big regard. What's that?
Oh, there's more than 3 levels.
So it's not a 1-to-1 ratio in the charges, because calcium is a 2+, it's in group 2 on the periodic table, and fluoride is a 1-. So I have a different number of anion to cation ratio going on. Up to this point, it's always been 1-to-1. Now it's not. And then the other thing that stands out is there are more than 3 levels, and Yeah, we usually show that the packing of a unit cell is dominated by the anion, but it turns out that this one's just easier to see if we let the cations be in the columns. So let's do this. This is fluorite. And if you were watching the screen while I was pulling these unit cells up, what images were on the screen before they showed the unit cells? Did anybody watch? No? There were a whole, but they started out as rocks, and then they ended up being like gemstones. These are all mineral structures, and some of them are quite pretty. Use your chemistry words to tell me what the calciums in fluorite are doing. Describe the positions of the calciums to me. Okay, first of all, so far all we've seen are cubes, and I'm not going to show you anything that's not a cube. Spinel today is complicated and it might be distorted, but ultimately, yeah, it's not. I don't think it's actually cubic in the end. Everything that we're going to see is cubic. So this is some kind of cube. What kind of cube is it? See, the calciums are on every edge, on every corner. Because the calciums are on every corner of the cube, therefore this is a cube. Where else are the calciums? They're on the faces. They're at the center of the faces of the cube. Exactly where the chlorides were in sodium chloride, I now have calciums in this unit cell. So this is a face-centered cube. Fluorite is going to be a face-centered cube. Only now there's my cube corners, and then I need one on every face. One here, one here, one here, one here, and one here, and kind of one here. Face-centered cubic in terms of calciums. Now is where it gets kind of interesting. Where are the fluorides? I'll ask some questions. Are the fluorides at the corners? No. Are the fluorides at the edges? No. Are the fluorides at the center of the cube? No. The fluorides are somewhere else. The fluorides are here's a cube. I'm I'm going to divide that cube into smaller subdivisions. So I'm going to take the cube and I'm going to cut it in half on that axis and in half on this axis and in half on that axis. How many cubes do I now have?
8.
8. I have 8 cubes. How many fluorides can you see in the computer-generated picture on the screen? 8. And where are they in relationship to each of these new individual cubes? They're at the center of these cubes. So I have a fluoride here and here. And here, and here, and here, and at the back, and at the back. Okay? I think I could probably push that one back a bit. There you go. There's one fluoride in each cube. So if I think, okay, let's look at my octahedral center. That kind of divides things a bit. Back somewhere, I'm a little bit off with that black dot. Here. This is why we end up not going to these all the time. So there's another one back there. I think that's all of them except this one down here. Okay. That's kind of complicated. But there is a fluoride at the center of every cube. If, for sake of clarity, now that I've written it out, for sake of clarity, I said, I don't want to think about everything just now. Let me think about only one of those sub-cubes. I'm only looking at this one sub-cube. Can make it a little bit better now. There you go. I guarantee that you know more about this than you realize that you know. tell me what it is that you can see about the geometry of the black dot there that is representing our fluoride. It's tetrahedral. There is an atom, in this case ion, at both diagonals on the top of the cube, and then on the bottom part of the cube there is an atom, now ion, at the other corners. If there is an atom in the center of the cube, then its relationship to the corners is tetrahedral. The fluorides are in tetrahedral holes. This framework, the face-centered cube, sets itself up that at the center of those 8 quadrants, quadrant really means 4, quadrant at the top and quadrant at the back, quadrant at the top, quadrant at the bottom. I've got 4 fluorides completely inside the unit cell, and every one of them is tetrahedral because it is close to 2 down and 2 up of these opposing charged ions. Okay? So, the fluorides are in the tetrahedral holes, and the calcium makes a face-centered cube. Let's do a couple of things with this information. First of all, let's count occupancy. Occupancy, we've done this before. Here's the calcium. How many corners do I have? 8. How much of the sphere is inside the unit cell if it's at a corner? 1/8. The calcium also is on the faces. How many faces does a cube have?
6.
And how much of the red sphere is inside the unit cell if it's on the face? So I have 4 calciums but remember, each calcium is a 2+, which gives me a total charge due to the calciums in this unit cell of 8+. Let's look at the fluorides. How many fluorides were there?
8.
Where are they?
Inside.
They're inside. And the 8 pluses and the 8 minuses match each other. So we're good. All right, let's break this down and see what its projection looks like. We might get it all in one. We might have to break it into layers. Okay, let's look what I have. The very, very bottom is layer 0. The very top is layer 1. In the middle, where the face-centered calciums are, is layer half. What layer are the fluorides on?
4 and 3.
Okay. Let's see if we can do it. I'm going to erase this because we've already written the occupancy stuff down. I'm going to do it so that my projection can be close to my unit cell diagram. All right, nice and big and clear. I have cations at every corner, and they are at the 0 and the 1. I also have cations at the center of the top and bottom face, and they are at layer 0 and 1. And then I have cations on the other 4 faces, the remaining 4 faces of this cube that are the front, the back, the left, and the right. And they're here, and they're going to be at layer 1/2. And then, looking from the top down, I can see this fluoride, and completely underneath it is another fluoride. So they're going to eclipse one another, and I'm only going to show you one of them. I'm going to label both of them, but I'm only going to show you one of them. And this one is on top of that one, and this one is on top of that one, and this one is on top of that one. Drawing skills are not that bad. And they go here. And they are at 1/4 and 3/4 and 1/4 and 3/4 and 1/4 and 3/4 and 1/4. Okay. That one actually turns out to be easier to see in the projection than just regular face-centered cubic, because I don't have occupancy, I don't have like occupancy on the same vertical. They're separated out. And then this has 2 up and 2 down. So these are tetrahedral holes that are left in the lattice. So the lattice makes a space, and then it leaves holes where the other ions can be. Okay, that's fluoride. do spinel. Let's look, maybe, oh, okay, cool. Let's do perovskite. What's my best one? Okay, this is a mineral called rutile. Rutile is titanium dioxide. Titanium is, oh, I've got a periodic table. Titanium is here on the periodic table. Well, wait, can't see. What am I doing? There you go. On the periodic table. Potassium, calcium, scandium, titanium. Because it's a transition metal, it has variable oxidation states. It has a +2 that's widely available. It has a +3 that we see from time to time. And it has a +4, which is its maximum. And in the +4, it makes an oxide that is TiO2. And TiO2 does this. And rutile turns out to be a hybrid of body-centered cubic and with tetrahedral holes. So let's take a quick look at that. It's kind of a odd one. Rutiles, page 114 in the book. So rutile is going to be our first example of a unit cell that is not perfectly cubic. And is a little oddity. Give you the names of the deviations from cubic. Got a little table for it in the book. Common deviations are rhombic and orthorhombic. By the time you get to the monoclinic, I think you've kind of you've got a little bit too much variation in your structure for us to worry about. Okay, so rutile is titanium oxide, and it is not cubic. Again, I'm going to, just because of convenience, because the way that it comes out is visually easier to understand, we're going to put the titaniums at the corners. there's a titanium at every corner. And then there's one at the center. Right. Oxygen has I almost said it has a fixed oxidation state. In general chemistry, it has a fixed oxidation state. 2 minus for oxide. 4 plus for the oxygen. All right, this gets kind of complicated. That on the diagonal between the two titaniums, I'm going to put an oxide, and they're going to be on the face. On this diagram, the one that's on the screen, the ones that are on the face are these ones. And it's not quite the way I'm going to represent it. And then I'm going to have some that are inside the body. So I have on the face.
Which face are they on?
Top.
Okay.
This is 1, and this is 0. I'm going to have oxides be on the face of layer 0 and on the face of layer 1 inside of what is a distorted body-centered cube for the titaniums. And then I have because those ones went diagonal, I'm going to build an oxygen now, but it's going to be completely inside between here. And then out here there'll be another one inside. And it sits between that one, and this one. Titanium, titanium, titanium. Equidistant between those 3, I've got another oxygen here. Okay. And they are going to find themselves, because I'm equidistant from here, these two, and that central titanium, it means that I'm on layer 0, half. Okay. So now, not a cube. Let me see if I can make it be. Demonstrate that it's no longer a cube. But I have ions at these corners at 1 and 0, 0 and 1, 0 and 1, 0 and 1. I have a titanium at the body center. And then I have oxides on this diagonal that are on the top layer and the bottom layer. So this is a 0 and a 1, and that is a 0 and a 1. And then I have oxides this way. They're on layer half. figure out what we've got. The titaniums are 4 pluses, and I have 1 at every corner. Plus I have 1 at the center. I have 8 pluses. Let's look at the oxides. There are oxides on the faces of layer 1 and layer 0. How many oxides are on the faces of layer 1 and layer 0? 4. And how much of the sphere of the ion for each of those oxides is actually inside the unit cell? If you're a face. 4 halves equals 2. And then I have these 2 oxides that are completely inside the unit cell. I have 2 internal, which is 2 times 1 equals 2. And 4 times O2 minus is 8 minuses. Pluses and the minuses cancel each other out. And we're good. Okay. That ate up a lot more time than I was thinking it was going to. Let me just show you a couple of other things that are regular textbook examples. Perovskites, page 116 in the book. Yeah, okay. Let me see if I can find a diagram. Actually, the book, actually this one's not so bad. So, here's perovskite. And perovskite has 3 different ions in it. They can be individual elemental ions, or sometimes they can be compound ions like ammonias or other things like that. But I have 1 ion completely at the body center, and then 6 ions around it in a tetrahedron, and then 8 different ions around that in the cubic corners. So perovskite is another compound that we can do about this time. And then there's this, which is not in our book, which is a bit of a shame. This is spinel, and spinel is a cube, and then inside each quadrant, they're not quadrants, quadrants would be 4. What's the subdivision word for an 8th? If a quadrant is a 4th, what's an 8th? Octant. Inside each octant, you can get all sorts of crazy stuff going on. So here, there's a couple of examples. Let's look at this one. And I'm not going to bother putting this one on video because although this is my favorite, I doubt it's going to show up on the exam. And so inside each of those subdivisions, you can put another complete little unit cell. And sometimes they're little tetrahedra, and other times they're little cubes. And some of the space is left open, And so spinels, I did a couple of years on spinel for radiation resistant ceramics. That if you hit this thing really hard with nuclear radiation, it just rearranges the ions around. They just kind of scatter around inside the big unit cell. And that just absorbs the momentum of the attack. Really, really bizarre little compound. Okay. All right, so we've seen more odd, complicated unit cells. Oh, we just saw our first non-cubic. Page 92 of the book. You got cubic, you got tetragonal, and then you've got orthorhombic that are all based in the cubic world. Cubic, all the angles and all the sides are the same. Tetragonal, you have two of the sides be the same. One of them is unique, so it's rectangular cube now. And then orthorhombic is all the angles are still 90 degrees, but all sides are different lengths. There are unit cells out there that instead of being cubic, and I don't think we're going to go down this route, they start to veer to one side, and you get some, if not all, of the angles not being 90 degrees. We're going to keep ours in the framework of at least being founded in the cubic family. I'm wearing two sets of glasses. All right, let's get back to close packing. Part of our limitation here is our ability to draw consistent spheres or circles. And then our inability to convert two-dimensional projections back into three-dimensional shapes. We don't typically have too much of a problem turning three-dimensional shapes into two-dimensional projections. But being able to see what's going on here in reverse can be a little bit difficult. Not doing so bad. Here we go. Getting a little bit sloppy on that bottom layer now, but not quite touching. Okay, this is close packed, and if we find an atom ion, we find that it is surrounded by 6 others in a hexagon. And we have 2 common types of packing, and they are cubic closed packed and hexagonal closed packed. And because these are all clearly hexagons, people think this is going to be hexagonal closed packed. Not so fast. We're going to call this layer A. It's the first one in. This is layer 0. It's A. We call it A for a reason, because 0, if I build this and then I turn it at an angle, 0 and A becomes something slightly different. Okay. Layer B is going to sit on top of layer A. And we showed you this the other day. That if you let them self-assemble and pack, there's the hexagon, right? So my next layer doesn't sit on the peak of the 2 spheres, it sits in the dimple. So the question is, what's immediately below, so this is now going to be layer B, what's immediately below the sphere of layer B? Immediately underneath it? Nothing. It's a gap. It's sitting above a gap. So B goes here. And it sits right on top of that gap. And if I draw enough of them, they should all be centered on that gap. And of course, they themselves will form this little hexagonal packing, and at the center of each of your red spheres, got a little bit sloppy here at the bottom, there's a gap at the center of that sphere. There is a gap at the center of that sphere. Guess why I drew this so big? That's layer B. Here comes layer C. Layer C has 2 choices. So layer C has to sit in the dimple of the red spheres. Yeah? So here's enough of this layer that when my next layer goes in, it has to sit in the dimple. And if I look immediately underneath this layer C, what do I see? Layer A. But I could move it. I could, if I organize things a different way, I could have it sit somewhere else where I can see just the table. All right. So if my next layer, see this dimple? If I put my next layer here, and my next layer is A, I've gone back to making A's, and I put over the red dimple, over the red dimple, over this red dimple, I've made A again. And the A, B, A is called hexagonal close packing. If, however, I do something really, really tricky, we'll see if I can see it. Come on, let me find it. There is a dimple here, and a dimple there. And underneath that, this red triangle and the black triangle underneath it, they're pointing in slightly different directions. See this triangle? See that red triangle? The centers of them are over nothing. So if I put my new atom or ion here, that's now a new unique position. I have a layer A, a layer B, and a layer C. This turns out to be cubic. Here's why. And we're only a minute over. Actually, more than a minute over. I'll give it back to you. It goes here. All right, so there's nothing underneath these. So what I've got is a triangle, and then another triangle, and then another triangle. That's cubic close packing. If you take the cube and you tilt it, this, how many am I going to do? 1, 2, 3. I have a triangle that goes this way. And then underneath it, I've got another triangle going the other way. 3, 2, 1. And then here, I have this atom of ion, and it's in the center of that triangle. So I've got, if this just keeps going out, these are all hexagons. Look, 2, 2, and then 3, and then it would go back down to 2. This way, if I tilt this at an angle, these are hexagonal layers. This is layer A, B, and C. When I tilt it that way, it becomes a cube. It is not easy to see. We were going to do some of this in class. I spent a little bit too much time scribbling on the board. We will defer this to another day. But you'll all do it for credit. Something's different. Okay, the test. Molecular orbital of a diatomic ion, possibly cyanide, nitrogen, carbon monoxide, or any combination that is isoelectronic with it. So NO plus, OCl minus, OF minus, these are all things that you can If you can draw the molecular orbital of one, you can draw the molecular orbital of the other. What else do we do? Shapes of molecular orbitals. Maybe a tiny bit about valence bond theory. Names of hybrids. VSEPR. Names of geometries and the orbitals involved in them. Could be a small question, but the big question is going to be an MO diagram. You will have to draw an MO diagram. You will have to draw a unit cell, or given a unit cell, draw its projection, count its occupancy. Be able to spot what's octahedral, what's tetrahedral. Okay. Periodic trends, yeah. You should know ionization energy, you should know size, you should know atomic radius and ionic radius, and all of that falls back on Z effective. There will be a calculation on Z effective. If I ask you Z effective for an atom, I might follow that up with Z effective for the ion, and ask you what is the meaning if the numbers are now different, what does that mean?